In this class, we will discuss about Biot Savart law. And before we discuss it, I have given you some details of the electric charges and magnets related to their discoveries. Magnets, we know, it was discovered around 600 BC in Greece. Magnesia, it was discovered accidentally. And electrical charges, 600 BC, again in Greece, Thales of Miletus, amber attracts light objects after being rubbed with silk or wool. This was the first observation related to electrical charges. So both these phenomena were discovered around 600 BC, and till about 1820 they were studied separately. So electrical charges, they produce certain kind of effects in their surroundings, and other charges, if kept in that region, they respond to that, so they experience force. This is electric field. Magnets, they produce magnetic field around them, and if we bring another magnets in that region, they also experience force. It was in 1820 that a scientist, Oersted, Danish physicist Oersted, found a link between the two. He observed that charges can produce magnetic field, and later on it was developed, and then we got electromagnetic theory. What he did was, a battery, this is a cell or a battery, and then key. So current will flow like this, positive to negative, and if we bring a magnetic compass here, magnetic compass means a magnet, this is a very light magnet. So if we keep this magnet here close to this wire and we switch on the key, that is we close the key, when current starts flowing, there is a deflection in the magnet. So this needle gets deflected in a particular direction. And we have studied till then that magnets respond to magnetic fields only. So it means, it led to the conclusion that when current flows through this wire, then a magnetic field is produced. So this was given by Oersted experiment we call it. So whenever there is a current in the wire, there is a magnetic field in nearby regions. Biot Savart, they found a mathematical relation for the magnetic field produced due to a current carrying wire. On what factors it depends and all that. So let me take a wire and a point P. The magnetic field, if we represent it by B, so dB is, I am taking a very small section of this wire, say of length L, and then we will see on what factors the magnetic field produced by this small element depends. So experimentally they found that dB, the magnetic field due to this small element, depends on current in the wire. More current means stronger magnetic field. It also depends on the length of this part, proportional to this. So bigger the wire, more will be the magnetic field. It will also depend on this angle and inversely proportional to distance square. So just like Coulomb's law, here also the magnetic field is inversely proportional to the square of the distance. So this is the magnetic field produced due to this wire, a small section of this wire, ideal sin theta by r square. Now if We remove this proportionality sign, we will have a constant. And in SI system, we shall be taking SI systems only here. This constant is this is just like 1 upon epsilon naught in Coulomb's law, where we have mu naught upon 4 pi. This mu naught is called permeability. Their epsilon naught was permittivity, and they are related again. We will find out in due course that epsilon naught and mu naught are also not independent, they are related. So mu naught is permeability, naught means it is for free space. And if we have mu, this will be the permeability of the medium. And again, exactly in the same way, mu will be mu r into mu naught, relative permeability. We will do all these things. So mu naught is permeability of free space, and its value is 4 pi into 10 raised to the power minus 7 in SI system. We will work out the units and then we will write them. So this value, mu naught by 4 pi, it has a value of 10 raised to the power minus 7. So again see, there is a wire with current I, and we want how much magnetic field is produced by a very small section of this wire. Then it is I dl sine theta by r square. So it depends on the current, it depends on the length of that element, and it depends on the angle between dl and this length, and inversely proportional to this distance, square of this distance. So r square sine theta dl I. And when mu naught is coming, it means it will also depend on the medium, how much magnetic field is produced. Okay, so mu naught upon 4 pi I dl sine theta by r square. This is the magnetic field produced by this part, dl. Now units, this B has unit Tesla. We will again study in other chapters few more units about it. Gauss, that is also one of the unit of measuring the magnetic field. Then one is Weber per meter square in terms of the units of flux, magnetic flux. For the time being, it's enough. Tesla is SI unit of magnetic field. We also call it flux density, magnetic flux density. Okay. So now we can find out what will be the unit for mu naught. This is Tesla meter square upon ampere meter. So Tesla meter per ampere. This will be the unit for mu naught. Tesla meter per ampere. We can also find out the dimensional formula that we will do later. Now, whenever we keep a magnet, this is a wire and I keep a magnetic compass. So this compass or magnet will not align itself randomly in any particular direction, randomly. So it will always be in a particular direction. It means this force due to this current, this has a specific direction. Let us find out now what is the direction of the magnetic field, and then we will also see what is the direction of force on any magnet when we keep it in a magnetic field. Just like in electrostatics, when we keep an electric dipole, it tries to align itself along the field. Same thing happens here too. So whenever we keep a magnet in a magnetic field, it tries to align itself along the magnetic field. So let us find out the direction of magnetic field, and that will be the direction in which that compass will align itself. Every compass is a magnetic dipole. For this, let us write this in vector form and then we can find out. So dB in vector form, it is mu naught by 4 pi I dl cross r upon r cube. Now see how can I write. This theta is the angle between dl and r. So let me write r also. So dl sine theta r, and it becomes r cube, then multiply and divide by r. So dl r sine theta, that can be written as dl cross r upon r cube. So direction of B is now the direction of cross product of dl and r. dl is a length element. We have taken is a length element, and its direction will be same as of current. So this is dl. So this is dl, and this is r. This is theta. Well, how do we find the directions of cross product? Always cross product rule is you have to turn your fingers from first vector to second through the smaller angle. So dl cross r, it will be like this, right? So force is inward. Inward force is represented by a cross. Cross means the field is directed inward into the plane. If I take another point, say Q here, and we have to find direction of field at this. Now dl is here, r will be this. Let me call it r dash, and let us call it theta dash. So dl cross r, this will be like this, first vector to second. So this thumb points outward, and outward field is represented by a dot. Dot means the field is like this. Cross means the field is in. There are few other rules also to find out the directions of magnetic field. One is a right hand thumb rule. Hold the conductor in your hand, thumb towards current, and just curl your fingers. The direction in which the fingers are moving, that is the direction of the magnetic field. So if I hold it like this, when my fingers are towards this point, right, field is in, and same way this is out. So actually at any point, the field is like this. Here it will be in at that point. So it is like this, tangential to this circle. And this we can also call it magnetic field line. We will study in detail that too, but this is how we can draw the magnetic field line, because if any small dipole is kept, that will align like this. So here it will be like this, here it will be this, here it will be this, and here it will always be tangential to that circle. So this is how we can find out the direction of magnetic field. Either you apply this rule or simply apply the cross product rule, dl r inward, dl cross r outward. Okay, so magnetic field due to a current element is proportional to current, the length of that element, sine of the angle joining dl and r, inversely proportional to the square of the distance. The constant of proportionality is mu naught by 4 pi, having a value of 10 raised to the power minus 7 Tesla meter per ampere in SI units, in SI system, and the direction of it is perpendicular to dl and r, which can be found using either the cross product rule or the right hand thumb rule, screw rule. Okay, there are some other rules also, but cross product rule is the most general one. That is the best one. Or if we have a point which is perpendicular to this line, we can also use this. Keep the thumb in the direction of current, fingers towards the point where we need the field. Direction of palm or push, this gives the direction of the field. So field is in. If I take this point, field is out. But in this this point is always at 90 degree to it, but here it is not. So this is the most general cross product rule. Okay, now we can find out the direction of the magnetic field in some particular cases. They may be useful for you when you are solving the numericals. Suppose we have a circular current carrying loop, then find out the direction of the field at P. Or if I have current carrying wire like this, then find out the direction of the field at A and B. Or, okay, I will take one or two more. In this case, first consider any small element, and whenever you have a closed loop, the direction of field due to each element comes out to be same. So if I take a small element, I can use this rule, field is out. I can use this, even then the field is out. Any element taken here, holding like this, when we are here, the fingers are moving out, so direction of field is out. Direction of field is out. So you can take 3-4 random points and the field is outward. For this, so when point is this, inward, A, outward. So B, field is cross, A, field is out. So point. Okay, one or two. In this case, it is a little bit complex. I have given you a square loop which is kept like this. It is kept like this and the point is here on the axis. I'm asking you find out the field due to PQ. Now see this very carefully. This is like this. So P, Q, and then we have, oh no, Q, P, then R, then S. Current is coming like this. So when the current is like this, you can apply this rule, thumb towards the current, fingers towards the point. Now you are not supposed to keep like this because this point A is down. This field will be this, perpendicular to this. So if I connect this to this, field is perpendicular to it. Find out yourself. Apply this rule yourself to find out, only then you will be able to master it. Same way if I ask field about this, so here the current is this, in, but the point is there, perpendicular to it. So this will be like this. For this, current is down. So it will be like this and this. So actually it sort of cone is formed of all these vectors. This is like this. So if we resolve them all, these components will cancel out and all will have one component in the same direction. So I can say the field due to the loop will be along the axis. This example should be done by you 2-3 times at least to understand what is the direction of current due to each part and then what will be the direction of the field due to the full loop. This is, I'm again telling you, the current towards you. This is the easiest to apply here, and then fingers towards the point perpendicular to it. For this, so if I resolve this, one component this, one component this. One is this, if I say this is theta, so it becomes dB cos theta. This will be dB sin theta. Same way this will become again dB cos theta, and this is dB sin theta. So same way all perpendicular components, perpendicular to the axis, all these components will cancel out and net field will be this. All these cos components will be added. So it's all about Biot Savart law. Next time we will take up the applications of Biot Savart law. The first will be to find out the magnetic field at the center of a circular loop, and we will take up the two cases, one at the center and one on the axis for circular loop.